This unit focuses on an important type of reaction of alcohols, and that is oxidation. This particular reaction is relevant both in terms of chemical synthesis and also in terms of biology, because a variety of biologically relevant reactions involve the oxidation of alcohols. So we first need to lay the groundwork for looking at those reactions by talking about what we're referring to when we describe the term oxidation. So thinking back to general chemistry, when we look at oxidation and reduction in general chemistry, we typically think of oxidation as a loss of electrons and reduction as a gain in electrons. And when we think about this in the perspective of general chemistry, we're often dealing with inorganic ions, such as converting iron 3+ to iron 2+. And we would describe that as a reduction because the oxidation state, 3+, is being lowered to +2. And therefore we describe that as reduction. In organic chemistry, it's a little bit less clear when we look at oxidation and reduction because we're not typically dealing with ions. Instead, we're typically dealing with molecules where we have no formal charges, such as comparing alcohol molecules to aldehydes or ketones or carboxylic acids or alkanes, etc. And so generally when we're looking at oxidation in terms of organic chemistry, what we're looking at is defining oxidation as increasing the number of bonds between carbon and an electronegative atom, such as namely an oxygen or halogens, or a loss of hydrogen from the molecule. Reduction, on the other hand, is bringing in more hydrogen into the molecule, losing oxygen, or losing halogen atoms. So we can apply these terms of oxidation and reduction to the typical types of organic molecules that we'll be looking at in the next couple of units. Namely, if we start with an alkane that has a primary carbon atom as the carbon that we're focusing on, we would say that that carbon has become oxidized if we replace one of the carbon hydrogen bonds with a carbon oxygen bond, because that's going to correspond to both decreasing the number of carbon hydrogen bonds and increasing the number of carbon oxygen bonds. So let's show what would result from replacing that carbon hydrogen bond with a carbon oxygen bond. So when we replace that carbon hydrogen bond with a carbon oxygen bond, we end up converting our primary carbon that was oxidized into a primary alcohol. And we can put in brackets above the arrow here just an O in order to indicate that oxidation has occurred and going from starting material to product. We can then further oxidize a primary alcohol by continuing to increase the number of carbon-oxygen bonds that are present. And in order to further increase the number of carbon-oxygen bonds present, what's going to happen is that the hydroxy group gets converted into a carbonyl group. Conversion of that hydroxy group into a carbonyl group is going to require that one of the two hydrogen atoms, here or here, be lost in that process so that the carbon in the center here doesn't end up going over the octet rule. And so as a result, in our product, we're just going to have one hydrogen atom left directly bonded to that carbon that's being oxidized. This molecule, of course, we would refer to as an aldehyde functional group. So primary alcohols will get oxidized into aldehyde products. Then from there, the aldehyde is still going to be susceptible to additional oxidation, further increasing the number of bonds between carbon and oxygen. And we'll again do that by removing a carbon-hydrogen bond and replacing it with a carbon-oxygen bond. And in this case, the carbon-hydrogen bond that we have left available, the carbon that's being oxidized, is we have this aldehyde hydrogen right there. So we'll replace that with an oxygen, and that's going to lead us to a carboxylic acid product. So we would certainly describe this conversion of the aldehyde starting material into the carboxylic acid product as oxidation, because we've increased the number of carbon oxygen bonds in going from our aldehyde to our carboxylic acid, because we replaced that hydrogen atom there with a hydroxy group. And at this point, this is generally the end of the road here, because the oxidation reactions are generally going to convert carbon hydrogen bonds into carbon bonds with oxygen. And you'll notice here that based on the structure that we have drawn, we have no more explicitly shown hydrogen atoms that are bonded to carbon in order to be lost for an oxygen to come in and complete the oxidation reaction. So this is the very typical paradigm that we'll see in oxidation reactions, is that we're going to take the carbon that's being oxidized, which is this carbon here that we're focusing on in our primary alkane, and we're going to replace carbon-hydrogen bonds with carbon-oxygen bonds, going from the alkane to a primary alcohol. Primary alcohols will get oxidized to aldehydes by replacing one of their hydrogen atoms with carbon-oxygen double bond that we see here, and then further oxidized to incorporate the additional oxygen atom that we see appearing in the final carboxylic acid product here. At this point with the carboxylic acid, we have no more carbon-hydrogen bonds available, so we can't further oxidize. Now this is the case that would happen if we started with a primary alkane, went to a primary alcohol, onto an aldehyde, onto a carboxylic acid, and so on. So what if instead of starting with a primary carbon, what if we started with a secondary carbon instead? How is that going to affect what we observe here? So the oxidation of our secondary carbon is going to lead to the formation of a secondary alcohol by replacing one of the carbon-hydrogen bonds here with a carbon-oxygen bond. So let's go ahead and draw the product that would result from that, which will be a secondary alcohol. So we have effectively removed the hydrogen atom that was bonded to the carbon and replaced it with a carbon hydroxy group bond. You'll notice now that we still have one carbon-hydrogen bond left, leading to right here, and so therefore we can do another oxidation to replace that carbon-hydrogen bond with an extra bond to an oxygen. And in following the trend that we saw up top where we converted the alcohol group into a carbonyl group, we're going to do the same thing here. When we remove this hydrogen right here, we're going to replace that with the carbonyl group. So we'll be converting the hydroxy group into a carbonyl group as a result of this reaction. So we removed the carbon-hydrogen bond and replaced it with the extra carbon-oxygen bond to give conversion of the hydroxy group from the secondary alcohol into the carbonyl group. And you'll notice that the functional group this would fit would be that of a ketone, because keep in mind that those R groups are each carbon-containing group. So this would give us a ketone. Then we could try to further oxidize this. And remember that the key to oxidizing our carbon atoms here is replacing carbon-hydrogen bonds with carbon-oxygen bonds. And you'll notice here at the site that's being oxidized, that is our ketone carbonyl group, we have no more direct bonds to hydrogen available, and therefore we would generally see that this would undergo no further reaction, so this can't be further oxidized. So unlike the situation where we took a primary alcohol, we oxidized to an aldehyde. In the aldehyde, we still had a carbon-hydrogen bond left, and so we're able to further oxidize and replace that carbon-hydrogen bond with a carbon-hydroxy group bond to give a carboxylic acid. In the case of our secondary alcohol, we end up with a ketone rather than an aldehyde here, and that ketone can't be further oxidized because there's no more carbon-hydrogen bonds available at that carbon that's being oxidized, the carbonyl carbon. So we're stuck there with that. We can take a look then, thinking about different types of alcohols. We talked about primary, secondary, and tertiary alcohols before. So we could also think about what about oxidizing a molecule that is a tertiary alcohol. So we could take, and we'll start with a tertiary carbon of our alkane. So remember, these R groups represent carbons or carbon chains here. So in a tertiary carbon, we have just one bond to hydrogen, 3 bonds to carbon, hence tertiary. So in our tertiary alkane, we can go ahead and oxidize that. Remember that the oxidation, the trick here is to always convert carbon-hydrogen bonds to carbon-oxygen bonds. So we can convert our tertiary alkane starting material into a tertiary alcohol product through oxidation. And then we ask ourselves, can we further oxidize this tertiary alcohol? So in the scenarios above where we start with primary or secondary alcohols, we are able to convert the hydroxy group into a carbonyl group by replacing a carbon-hydrogen bond with that extra bond to oxygen to give the carbonyl product. Here, when we start with a tertiary alcohol, we have no more carbon-hydrogen bonds available at the carbon that we're focusing on, the carbon that's reacting here. And so therefore, under typical conditions, we would be able to generate no further oxidation, because further oxidation would require breaking carbon-carbon bonds here, here, or here, And that simply is not going to generally happen. Carbon-carbon bonds in these alcohol molecules tend to be very stable and very, very difficult to break. So under typical oxidation conditions, we would see that the road would stop here at the tertiary alcohol. You would not be able to convert a tertiary alcohol on further down the line to anything more oxidized typically. Now, so far we've been talking really generally about oxidation here with our mindset that we're replacing carbon-hydrogen bonds with carbon-oxygen bonds. What we're going to do in the next unit is take a look at more specific details of how we can go about these oxidations. In other words, what specific oxidizing agents would we use here rather than just putting O in brackets to indicate that oxidation is happening. So the O in brackets indicates that oxidation is happening, but it's not telling us what chemicals we would actually need to use in order to carry out that oxidation. So in the next unit, we're going to look at the specific details that lead to oxidation of these reactants to give the products that we see, particularly focusing on oxidation of our primary and secondary alcohols to give us aldehydes, ketones, or carboxylic acids as our intended products.